You ever see one of those technical interview questions that looks super simple, but you just know there's a trick to it? Well, today we're going to crack one of the absolute classics.
All right, so check this out. We've got this simple piece of Python code. It creates a counter, starts it at 0. Then it kicks off 2 threads. Think of them as 2 separate workers. Each worker's job is just to add 1 to that counter 1,000 times. So you have worker 1 counting to 1,000 and worker 2 counting to 1,000 on the same counter. So the big question is, when they're both done, what's the final number? I mean, it's got to be 2,000, right? 1,000 plus 1,000.
But then we actually run the code and we get 1821. That is definitely not 2000. Something is way off. It's like hundreds of our counts just disappeared in a thin air. Okay, but here's where it gets really weird. We run the exact same code again, and this time we get 1699. What? Run it a third time, you get another totally different number. So the problem isn't just that it's wrong, it's that it's randomly wrong. It's completely unpredictable. What in the world is going on? Well, this little mystery has a name. The culprit here is something called a race condition. So let's dive in and define what that actually is. Okay, so a race condition happens when you have 2 or more threads all trying to mess with the same shared thing at the same time. In our case, that's the counter variable. The final outcome completely depends on the super random, unpredictable timing of which thread gets there first. They're literally racing each other to read and write that number. And the result is, well, it's total chaos. So to put it simply, the cause is a total lack of synchronization. The threads aren't talking to each other, they're not coordinating, they're just stomping all over each other's work. And the effect? Exactly what we saw. Completely unpredictable and wrong results because there's no order, no guarantee of who does what when. So how does this actually happen? Like on a micro level? Let's go investigate the crime scene. That one single line of code where all the problems are happening. All right, here it is. This is the absolute key to the whole mystery. That simple little line of code, counter plus equals 1. It looks like one single instantaneous thing, right? We call it atomic. But it's not. To the computer, it's secretly a 3-step process. First, it has to read the current value of the counter. Then it has to add 1 to that value. And finally, it has to write the new value back. And that little gap between reading and writing, that's where everything goes wrong. Let me show you exactly how an update just vanishes. Imagine the counter is sitting at 0. Step 1. Thread A comes along and reads the value. It sees 0. But before it can finish its work and save the new value, wham, the operating system switches context over to thread B. So now step 2. Thread B reads the counter. And what does it see? It still sees 0 because thread A never got to save its update. Now, step 3, the system switches back to thread A, which finally calculates 0 plus 1 and writes 1 to the counter. Great. But then, step 4, thread B does its calculation, 0 plus 1, and it also writes 1 to the counter. So did you catch that? We had 2 increment operations happen. But because they both started from the same place, 0, thread B's work just completely wiped out thread A's. The final result is 1, not 2. We literally lost an update. Now, imagine that chaos happening thousands of times a second. That's how we end up with those crazy random numbers. And this isn't some weird Python thing, by the way. This is a fundamental problem that can cause massive issues, like corrupting a database or crashing a website. Okay, so how on earth do we fix this mess? Well, thankfully, there's a hero for this exact situation. In the world of multi-threading, it's called a lock. So what is a lock? It's basically a tool that you use to protect a critical section of your code. And the critical section is just that vulnerable part where we're changing the shared counter. The best way to think about it is like a bathroom stall with only one key. A thread has to grab the key, we call that acquiring the lock, before it can go inside and mess with the counter. While it has the key, no other thread can get in. They have to wait outside. When it's done, it puts the key back, releasing the lock, and the next thread in line can go. It forces them to take turns nice and orderly. Okay, enough theory. Let's actually put this lock into our code and see it work. It's time to close this case and finally get the right answer. Check this out. The fix is actually ridiculously simple. On the left, you've got our broken, unpredictable code. And on the right, the solution. The only thing we added was that little with lock statement. That's it. That one line tells Python, hey, before you touch this next line of code, you must acquire the lock. And as soon as you're done, release it.
This makes sure that whole three-step process, the read, the add, the write, happens all at once as a single uninterruptible unit.
So now, for the moment of truth. We run our new protected code, and what do we get? A perfect, beautiful, predictable 2000. Exactly what it should have been all along.
And it's not a fluke. You can run this 100 times, 1,000 times. You're going to get 2,000 every single time. By making those threads take turns, we've totally eliminated the race. The outcome is predictable, the mystery is solved. So let's boil this all down. What's the big takeaway here? If you get this question in a technical interview, here is your cheat sheet. This is everything you need to know. It's super simple. The problem? It's a race condition. The cause? Multiple threads trying to access a shared resource without any coordination. And the solution? You've got to use a synchronization tool, like a lock, to make sure only one thread can touch it at a time. And really, that's the most important thing to remember. If you see something like this, the key is to identify it as a race condition and then immediately say the solution is synchronization, using a lock. That shows you get the what, the why, and the how to fix it. So I'll leave you with this thought. Where else might these little race conditions be hiding in the code you work on every day?